All right, so good evening. Hope that everyone is doing okay as can be and keeping safe. All right, today we're going to continue on the topic of system characteristics, and we're going to look a little bit more on system characteristics and analysis. So, in this presentation, we're going to be looking at a term called dominant poles. So we looked at poles in the last section, in the last presentation. We look at a term called dominant poles. We're going to look at first and second order approximation, and then we're going to close off looking at steady state error evaluation. So we know that the poles are any values of s in a transfer function that will make the transfer function tend to infinity. So here it is now that we're saying that higher order systems may be simplified, may be reduced to a lower order system by considering only the dominant poles. All right, so we know that it's not difficult for us to analyze first order systems and second order systems, and we have not looked at the analysis of third order systems. But beyond that, beyond second order, right, it becomes more difficult to analyze. So the argument that I'm presenting here is that when we consider dominant poles, we're talking about poles that dominate the behavior of a system. So again, we recall that last week we looked at the effects of poles on the system response. We saw that when the poles moved a particular direction, we saw changes in the step response of the system. So what we're seeking at here is to say, okay, which of the poles in the system dominate the response? Which of the poles are creating the most lasting effect or the most dramatic effect on the system response? And then therefore we'll consider those poles and neglect the others. That's the whole thing about dominant pole selection. So the argument here is dominant poles are the poles of the transfer function that dominate the system response, right? So these poles will give rise to the longest lasting terms in the transient response. So the other, we'll call them, if I want a better word, non-dominant poles. These poles, the response of them die out quickly. And so it's the longer lasting responses that will really show up in the analysis. So we're going to look at how this is done. All right. So the transient response of the system without the faster responding poles, those with much further away from the complex axis. So what we're going to find is that when the poles are further away from the imaginary axis, their response die out quickly. All right, their behavior die out quickly, and so what you end up with is that these poles are not considered dominant poles. So let us consider a third order system. All right, and here we have um, one real and two complex conjugate poles from this expression here. Let's present it as such. Having considered this third order system, what we're saying is this. A general rule is that any pole that is greater than 10 times the smallest pole would basically ignore that pole. All right. So any pole that is 10 times the smallest pole may be ignored. All right. And we're talking about the real part of the pole, the real part of, well, let's call it the pole for now, right? Pole. And essentially, we're looking at the real part of that pole. Okay. When we speak about being 10 times, we're talking about the real part of the pole. Now, if zeta omega is greater than 10p, then the system may be approximated to a first order system. If zeta omega is less than 10p, then the system may be approximated to a second order. Let us look at an example and see if we can bring this to light. All right, so here we have a third order system, okay? And the poles here, you quickly can see the poles in this system. All right, there are no complex poles in this system. So here are the poles. We're going to call them P1, P2, and P3. It's a third order system. So we have P1 being -1. And by the way, there's no structured way. There's no structured way of labeling these poles. All right, you could just simply list them out. All right, so there's no means of saying P1 equal -1 and or -1 and P2 equal. You could say P1 equal -25, P2 equal -1, and P3 -2, just for the record. So here are the dominant poles. Sorry, here are the poles, sorry, of the system. Now, if we carefully examine the poles in terms of their proximity to the imaginary axis, we can recognize that there is one pole that is quite a bit further away from the imaginary axis, as being P3 as labeled on the slide. And if we should use the rule that we just looked at, meaning that poles that are 10 times further away from dominant pole, so to speak, can be ignored. So we could start with the poles that are nearest to the imaginary axis. We look at -1, look at -2. So therefore, let us ignore -1 because it's the closer one to the imaginary axis. So clearly that is a dominant pole. But let us look at P2. P2 is -2. And when you look at -2, 10 times -2 is -20. So therefore, P3 would have completely satisfied the rule that we looked at earlier, in that that third pole, P3, is over 10 times further away from P2. Hence, we can ignore that pole and only consider the other two, P1 and P2. P3 is definitely far away. Dominant poles would be P1 and P2. So now, having said that, yes, the new system that we'll now use to represent the original system, yes, we're now approximating them because the third order system is a little bit more difficult to analyze. The aim here is to use the whole thing of dominant poles to approximate the original system with a lower order system. So here we're seeing that the original system, which is a third order system, can now be approximated to a new system that is second order. All right, and here we're seeing that we are approximating it to 15 over S1 times, sorry, S plus 1 all times S plus 2. And we just simply multiply it by 25 in the denominator. But there are other ways to address that. All right, so that's the approximation that we're looking at. Okay. So here, what they're doing here is to keep the system gain. That's why we're putting back the 25 to maintain the system gain. All right. So both systems will have the same system gain. So what we're seeing here, I'm not sure if you can see, if you could zoom in a little bit to get a better view. But what was just done is that we plot both systems response, step response, and you can see that there's no significant difference. I don't think you can even see that there's a difference in the plot. All right. So what we have just found is that yes, the system response is very close to that of the previous system. So both G and G prime, which were the two, the original system and the simplified system, they have the similar response. So in terms of analysis of control systems, this could be one of the tools that you would utilize in your analysis. Let's now look at steady state error. And we did cite steady state error as one of the characteristics that is used to assess the performance of a control system. All right. And so we appreciate that steady state error occurs in the steady state response. All right. We know that there are two responses in a system. We're talking about, on one side, we have the transient response, and the opposite side, we have steady state All right. Now it is in steady state that we have or we observe the steady state error. And so we're going to look at how we can evaluate the steady state error in a system. So given a system like this, and we're just going to keep it simple. Here we have what we call a unity gain feedback system. And again, a unity gain because the um, feedback loop can be represented as a block with one in it. Whenever you have a feedback loop that is linking the output directly to the summing of the input, it's just simply called unity gain. All right. Now, the steady state error, we're going to abbreviate that with E subscript SS. All right, steady state error due to an input change is given by this expression right here. So essentially, steady state error is the limit as S approach 0. There's an error right there. Let me cross this out. So this need to come out. All right, that need to come out. So the steady state error is the limit of S times E of S as S approach 0. So we're talking about the limit of the function E of S times S as S approach infinity. That's the steady state error. Now, this is equal to, considering this system up here, it can then be written as steady state error is equal to the limit of S times R of S over 1 plus G of S as S approach 0. Okay, that is the expression for the steady state error. Now, I could easily ask you to prove that E of S, yes, E of S is equal to what we have right here. Can I ask somebody to share with me how would you find E of S? Can anybody tell me how would you find E of S? How would you find E of S?
Could you use the block production method, sir?
All right, so you're proposing block reduction. How would you do that? You want E of S.
That would be
How do you find E of S?
that would be G of S over 1 plus 1 times G of S.
All right, I'm going to write what. All right, remember what I believe you're now proposing is block reduction technique, and what that technique is going to do is to close this entire thing here into a box where the input is R of S, output is C of S. But what we really want is to find out what E of S as a function will look like. All right, we want to know what E of S as a function look like. All right. Um, you want to comment again further? I could take another comment. I see Buchanan raising hand. Go ahead, Buchanan.
So we can find EFS by writing an equation for EFS and then transposing. Because if we look after the set point before, well, how to describe it? Where the circle is after the circle, the input
Hmm.
going into GS would be E of S. So yes, right there.
Okay. All right. So how do you propose that we find that now? How do we do this? Can you suggest anything?
All right, so if we look at it properly, the first input would be in RS. So EFS would be equal to RS,
Hmm.
then
I'm just gonna
minus
put R because I don't have enough space. Go ahead.
is equal
Minus.
to
Go
minus
ahead.
minus G times C. Well, minus CS or minus
Okay.
CS is going to be
Hmm.
equal to ES.
Equal to
Then
E.
then CS is going to be equal to ES times GS.
Okay.
All right,
All right.
and
So, very good. And so we
um,
can now substitute.
yes, we can substitute then transpose.
Hmm. Hmm. I didn't actually. All right, so we proceed along that line. All right, good suggestion here. Thanks. Crossdale, go ahead.
Sir, I was actually gonna say the same thing based on what you had before. The
Mm.
error signal would be the difference between the input and basically the output.
All right,
So
you want to proceed to break this down then? How would you take it from here to make? So what I could ask you is to just define, um, well, we could do it in a number of ways. The error signal in respect to the output signal. So we're not interested in the input. We're looking at error with respect to output. So how would you proceed?
okay, sir. So it's a we just transpose the formula since we have C now, and E of S would be equal to R of S minus E of S times G of S.
Hold on, I think I missed you. I remember I want to get rid of C. So couldn't we just put this up here?
Yes, sir. That's exactly what I just said, sir.
Okay, all right. Sorry, I missed part of what you were saying. Great. So we'll end up with, and again, I'm going to write it here, R minus E G equal E. That's it. And so if we now bring the E components together, what we'll have is R equal E, and this becomes what now? G plus 1, G plus 1. And so what we'd see now, if we bring this back over, it becomes E, right? We're just going up here. It's equal to R over 1 plus G.
Yes,
All
sir.
right, so thank you. Thank you, Kristen. So we will just prove that E of S here is R over 1 plus G, all right? And in this expression, it is specific to this system. Let me erase some of this work here. What we're looking at here is that this particular formula is specific to a system like that, a unity gain system. If the system had a feedback, a non-unity feedback transfer function, then of course the expression would look differently. But it wouldn't be a problem for you to derive that expression for E of S.
So,
Okay, go right ahead.
sir, would the only difference be multiplying G of S by H of S in that formula?
G of S by H of S.
Yes.
Um, I can't quickly pick it up right now, but I know how I would have the same procedure that we used just now in deriving the E of S. I would just simply consider, I'm not exactly sure, or I'll be able to project in my mind where it would end up, but that's something you can actually try on your own by just simply putting in a block here that you'd call H and see what happens when we begin to work it through. But um, that's fine in terms of your projection and your thoughts, all right? But I'm not able to project in my mind where that is. But the procedure is clear how we would go through to do that analysis, all right, or that evaluation.
Okay,
However,
sir.
for what we have here, yeah, man, good. So for what we have here, this is the form that we use. And note that what we're doing here now is to multiply S, or should I say multiply E of S by S. I particularly want to put it that way. We're multiplying E of S by S. Okay, so we notice that we have R over 1 plus G times S. And what we're going to do is to find the limit of that function as S approach 0. That is what we're going to be using. So the steady state error due to, in a particular case now, due to a unit step is given by, we know E of S is equal to the limit of S times E of S as S approach 0. But in this particular case, for a unit step, the input R of S is equal to what? 1 over S. That is the Laplace representation of the step input. So now we'll replace R of S with 1 over S because it's specific to the unit step input. All right. Now we're going to look at an example. So if we're saying here for a unity gain feedback system with forward path transfer function given as such. It says find the steady state error due to a unit step input when k is equal to 1. Now, the other part of the question says what value of k will result in a steady state error of 5%. So here we will notice that, I hope you notice that we're able to do some form of analysis, even design work. So if we had a system and we had the choice, or we were able to select the value of k, here we're seeing that we can use some analysis to evaluate what value of k would satisfy a particular steady state value. All right, in this case, 5%. All right, we're going to see if the solution actually exists. So let's see the solution. Right, so again, we clearly remember the formula for the steady state error, and we're talking about a step input, a unity step input. So we're now applying the formula S over 1 plus G of S all times 1 over S. And so we're now going to notice the substitution that we're going to be doing. So carefully note that we have S in the numerator, 1 plus, we're putting the transfer function now, which is G. G is the forward path transfer function, multiplied by 1 over S. And what we're going to see now, this is the part that I believe you will remember. There's some course that you'd have done that speak about limit, how to find the limit of a function. So this particular function is straightforward in the sense it's not a complex, well, I shouldn't say complex, but this arrangement of the expression, it is not difficult to evaluate the limit as s approach 0. Okay, so what we could do here is, I'm not even going to ask you if you do this in course, I'm going to believe that it is done. So you're going to substitute 0 for s. As I said, it's not going to do all the time. In this particular case, it can be done in this way. And I'm sure you would know that as well. So you substitute s equals 0. And so this becomes 0, this becomes 0. And what you end up with here is that you have 1 plus 1, because the 2 over 2 is going to give you 1. So it's going to be 1 plus 1 give you 2. So it's going to be now what? 1. It's going to be, and by the way, look carefully here that this section here is going to cancel the s up here. All right. So what we end up with is a result being 0.5 or a half. That's the steady state error. All right. So the steady state error is 0.5 or 50%. Now I have a question. If it is that we apply a unity step input in the system and the steady state error was observed to be 0.5, what then is the steady state value? What then is the steady state value? That's a question. All right, go ahead, Crossdale.
Would it be 0.5 as well?
Correct. That's very correct. Thank you. So if it is that we have a system, I'm going to explain it here. And if our system, we apply a unity step input, all right, that's what we put in there. And the system did something, and we're not even, well, it's a second order system. So maybe there's going to be some, this could possibly be what it does. All right, I'm not saying it must be. And it settles there. What we're seeing here is that steady state error, and by the way, this is not drawn to scale, obviously. Try my best to make it look like that, but in terms of proportions, that is. So here we have steady state error being 0.5. That means you're 0.5 units away from where 1 is. Okay? Which means to say if this is 1 here and you're halfway here, that means you're halfway here as well. So that's going to be 0.5. So the steady state position is 0.5. And so just by doing that analysis, we are able to extract a number of things. We're extracting not only the steady state value, but by extension, we're extracting the steady state value. So we know where the system is going to settle or where it's going to settle after the transient operation. All right. So that's how we extract the steady state error from this. Now let us look at the other part of the question, where we are looking at what value of k will satisfy the 5% steady state error. So what we're going to do is to substitute 5%, and 5% is 0.05. So steady state error is 0.05. Equate it to the expression E subscript SS, and what we're going to end up with is something like this, right? Where this is now going to be equated to what we have here, okay? And we're doing a similar thing here. So we're substituting S equals 0, all right? And I'm repeating this because I don't want persons who may not be fully conscious of what I'm saying to just all the time substitute S equals 0. When we're doing limits, sometimes it's
Yeah.
not as straightforward as that. But what I could say is that in most of our cases, probably all the cases that we look at in control system in this module, it is going to be of that form. But just be careful going forward. I don't want to be telling person's going to say, okay, you're going to choose 0 every time here, limit approaching 0. But it's okay to do it here. All right, it's okay to do it in this case. You would not do it in a case like this, just for the record. I just feel like doing this. You can't do it in that case. You can't just throw S equals 0. And I hope you see why you can't do that. All right, if you were supposed to find the limit, S approach 0, you couldn't just throw 0 into S in that expression. So I think I made the point clear now. So in this case, it's quite fine. You can do that. So this goes to 0, this goes to 0. And what do we end up with? We end up with, and of course, on the numerator, the 1 over S is going to cancel here. And so we end up with what? 1 over, and of course, the 2 here is going to do that. So we end up with 1 over 1 plus k. All right, and that should be equal to 0.05, all right, 0.05. So it's a matter of just transposing, making k the subject, and when we do that, we recognize that we have k is equal to 19. All right, k is equal to 19. Let me see the time, 7:35. Let us write down this, and I'm going to see if I could drop this into MATLAB quickly. So the original function, let me go back here. I'm going to drop it into MATLAB and see what we can do. The original function is g of s equal 2k over s squared plus 3s plus 2. All right, and I'm going to now go see if I could bring up MATLAB. I'm going to bring up MATLAB and do a quick analysis. So you remember what we had here. We're going to use k equal 1 and k equal 19 and assess what we just did in terms of the mathematical analysis. All right, so we're going to use the software MATLAB, which you would have been using in your lab exercises. So let me just quickly bring this up. Let's bring up MATLAB. Application screen. Okay, where is my MATLAB? Let's try this again. Right. All right. So I take it you can see my screen now. You just confirm you can see MATLAB, by the way. I'm sorry, MATLAB. Can you see the MATLAB screen?
Yes, sir.
Thank you. Thank you. All right, so I'm going to define the function that we just looked at. I'm going to define two functions. I'm going to call G1 the original system. All right, the original system. And that is when k was equal to 1. So we're just going to put, and sure, you can just follow through and see this is what you're accustomed to when you're doing your labs. 3, 2, closed. That's our transfer function, right? So that should look familiar. The other system that I'm going to define now, maybe I could just go up here and do this. Let's do it a long way. So Let's do G2 equal, and new system now of K equal 19, so that's going to be 38. All right, so it's 38. Oops, let's click here. Function and 38. I'm defining a system here. Numerator as 38, denominator polynomial s. I'm using that's 1, that's 3s, and then you have 2. So it's that. And so here we have the two systems being defined in MATLAB. And I'm going to now do the step response. Step G2. Let's get grid on that. See what happens. All right, therefore something went wrong. I knew something went wrong. I knew something was right. What I failed to do, and I hope persons would have seen this, and this is something that you need to look out for. Can anybody tell me what I didn't do?
So you did multiply the k equal 1 by 2.
K equal 1 by 2. No, I did that. I did that. But if you recall, what we're looking at here is the forward part. And sometimes it's in the rush that I'm doing it in. But I'm happy I made this error because I want to ensure that persons don't make this error. So what we're looking at is we're actually applying the function to G. But what we should do is to the closed loop transfer function. All right, to the closed loop transfer function. So without using MATLAB to do that, can somebody tell me what would be the case when we close this loop? All right, what would be the new transfer function? So let me go back. Well, not before you tell me what would be there. So we initially have, and you can write, let me go back quickly to, all right, fine. Look at this. This is what I have right here. I hope you can see the pointer. If not, you can let me know. I'm going to take up my, where's my,
Yes, sir. I see the pointer.
great. This would be the forward path transfer function, okay? You now tell me what you think the closed loop transfer function is going to look like. All right, so it's G over 1 plus G. It's a unity gain system. All right. Can anybody tell me what it looks like? What it look like, rather? Come on, guys. Nobody?
So wouldn't we need to know what the feedback is?
Well, I just said it. I said it's unity gain. Remember, it's a unity gain feedback system. So H would be equal to 1.
Okay.
Remember,
So
unity gain. Unity gain.
so it would be that, it would be 1 over.
All right, let's do this. 1. Okay. Don't think persons. Is there a
So it would be
difficulty? I'm not
plus,
able to see who's raising it. Whenever I use this, when I shift from the main screen, I can't see who is raising hands. So apologies, but you could just go right ahead and
Sir,
speak.
question.
Mm-hmm.
Sir, the original formula wasn't it supposed to be like 2 over 2k over the s squared plus 3s plus 2?
All right. Since yeah, I do believe it's a 2 because remember when I multiply the 19 by 2. So therefore, this new, thank you for pointing that out. Therefore, for G1, I just defined a while ago, G1, I would need to do it back over. Thank you for pointing that out. All right. I didn't plan to do this part, but I said, let me just try it and so you can see what it looks like in MATLAB, just to sort of build some confidence in terms of the analysis that we're doing by hand per se, okay, as opposed to using a simulation software. So transfer function, and quite rightly, it is in fact 2. So 2 would be up here, and so even the first one would have been incorrect. So thanks for pointing that out. And so we now have the denominator on, I think it's 3, 2. So the 2 plus so that would be 2 and the numerator 2 up there. So that would be 4. All right, that would be 4. Can anybody confirm that at the 4 when you do the closed loop? right? That would be 4.
There
All
would
right,
be
good.
just one plus the denominator.
1 plus, we said 1. That would be 3.
Yes, sir.
Correct.
Wait,
Let me go through. Since we're having some challenges, let me go back to the slide, and what we're going to do is to develop the closed loop transfer function. Then we'll come back to MATLAB and do this part. So let us stop bouncing back and forth. So let's stop this. Bring up back the slide, and then let's find the slide.
So for that transfer function a while ago, is that when you use a gain of 1?
Not could you the question you're raising? I'm not sure if I follow what you're saying.
All right, you added 1 to the numerator and 1 to the denominator a while ago, right?
Where's my pen? Yes. All right. Tell you what. Let me go through. Let us go through it together, if you don't mind. Here it is that we have a system, and we're saying that it's a unity gain feedback system. It's important to know that. And the forward path transfer function is that. It simply means that I can write this as my system. Okay, that's my system there. Cool. Now, when we're going to do the analysis in MATLAB, there's actually a programming term, or let's use that for now, that you can use to close the transfer function. But for now, let us not get into that. That's not the focus of the presentation. I just want to verify certain things. Let us close this and then apply it into MATLAB. All right, so the closed loop transfer function here, I'm going to use CL, closed loop transfer function, CLTF equal 1 over 1 plus G. Let us substitute. I'm sorry, G over 1 plus G. G over 1 plus G. Okay, too much sugar and juice. All right, so we're going to now substitute. And here it is, I don't have much space and it's quite obvious. But I know that what I'm going to end up with is the numerator as is in the forward path divided by what is in the denominator plus 1. So that was going to give us s squared plus 3s plus 2 plus, did I say 1?
so with the 2k plus 2k.
Hold on, I'm gonna go to the bigger screen. I want to make sure we get this clear. So I'm gonna come back to the wide screen. So we have, I'm going back to the wide screen. I don't have enough space here. So I'm going to go to a wide screen. All right, beautiful. So what we have here is G of s, let's do this quickly, equal 2k over s squared. I think we had plus 3s plus 2. And so we know that it is going to be G, right? And yeah, plus minus, okay? So now closed loop transfer function, I'm going to do it the long way now, is going to be G over 1 plus G, which is equal to 2k over s squared plus 3s plus 2 all over 2k over s squared plus 3s plus 2 plus 1. Now when we multiply both numerator and denominator by this term, as I suggested in the previous slide, then what is going to happen is that that's going to cancel, right? Up here, it's going to cancel. And when we multiply, so we're multiplying both numerator and denominator by this factor right here. I don't have the space, unfortunately, right? Too big, right? So this is going to cancel, and we multiply it by the what happened to my thing? Oh, interesting. All right.
Sorry, so
The entire thing just went out. Like my hand touched the mouse. There's no way to bring that back up. Anyway, all right, let's stick with it. We're gonna get through it. All right. 3s squared plus 2. Mm-hmm.
It's not sure it's supposed to be, sir.
I'm sorry.
Supposed to be
Yes,
three, not sure
I'm gonna
square.
have to fold over. I'm gonna fold over my laptop because I think my hand is touching the and it's touching the pad. All right, so I think a little bit smaller now. So it's 2k over s squared plus 3s plus 2, and that's equal to g. So when we now say now g, the closed loop transfer function that is equal to g over 1 plus g, therefore implies that 2k over s squared plus 3s plus 2 all over 2k squared plus 3s plus 2 plus 1. So essentially what we have just, go ahead.
So wouldn't it be easier to put 1 as s squared plus 3s plus 2 over s squared plus 3s plus 2
Easy in terms of what?
for calculation purposes, sir? To
No, what I'm doing is to go from first principle. So I hope you're seeing that.
yes,
So
sir.
we are aware that when you have a closed-loop transfer function, you have to apply this expression if it's a feedback. All right, it's a positive. It is a negative feedback, and so it becomes g over 1 plus g, because there's unity gain. If there was a feedback element, namely let's call it h, then it'd be g over 1 plus gh. So I'm simply going from first principle. All right. So here we're now substituting what we have up here down here. So up here the g, and the lower part would be 1 plus g, or g plus 1, whichever way you want to do it. All right. I turned the other way around, but it's the same thing. So this is g plus 1. Is that okay?
Yes, sir.
All right. So now what I had proposed to the group some time ago is to multiply numerator and denominator by this term right here. So when I multiply s squared plus 3s plus 2 over s squared plus 3s plus 2, which is 1. So we know we're not doing anything that is not mathematically sound. Now we're multiplying the expression by the multiplicative identity. Therefore, what is going to happen is that this part is going to cancel. Hope you're seeing that. And when we multiply this section here now, this is part we have to pay attention to. Okay, we're going to end up with, I'm going to try to fit it here. So we're going to end up with the closed loop transfer function being equal to 2k all over, watch this carefully now, this part here multiplied by what is here is going to leave us with 2k, right? And then you're going to have plus, everything is going to be multiplied by the 1 here. It's going to leave us with s squared plus 3s plus 2. So we can even write this in a more structured way, representing the common way we write transfer functions. So that would be s squared plus 3s plus, put in bracket now, 2k plus 2. All right, how is that looking now? Any concerns?
Looking good, sir.
All right, noted, Amanik. Anybody else? Any concerns? All right, so I take it that we're all okay. So what we're going to now do is to go back into MATLAB and to make our substitutions as we have it here, where we have one case where k equal 1, the other case where k is equal to 19. All right, so let's go back over to MATLAB now. So stop this. Application screen. I need to see my MATLAB. See MATLAB. All right. seeing my MATLAB screen. All right. All right, share. So now let's come back up here. I need to pull this over now. All right, so let's go now with our definition of our two systems. All right, so let's get down to this. We're going to call G1 the case where K is equal to 1. And by the way, it's not the simplest way to do it, but it works because it is still one of the ways to get it done. So we have, remember we had I hope you have on a piece of paper what we have as the closed loop transfer function. 2K over S squared plus 3S plus 2K plus 2. So I'm going to now substitute K equal 1. So it becomes 2. Close that off as the numerator. Then I'm going to define the denominator. It's 1, 3, and then because we have 2 times 1, that will be 2 plus this is 4. All right, is that okay? Persons who are following the journey. So that would be the transfer function with K equal 1. All right, let's go now with the other one. Please free to indicate if you have any concerns or if there are any errors in the procedure as I go along. So now the next definition is for the second system with K equal 19. I'm going to do that quite quickly. So that will be 2 times 19, that's 38. 38. Denominator now, we're going to define that. Again, 1, 3, and so that's 38 plus 2, that's going to give us 40. 40. This. Two systems. Now we're going to do step for G1 and G2. And then let's see what happens with this.
Sir,
Yes, go ahead.
should not be 3S instead of 2S.
Yes, in fact, yes, slip of the finger here. So that's in fact correct. When you put too much sugar in your drinks, you know.
Too much rum. John.
Oh, well, I'll leave you to ponder. All right, so we have 38. 8, I have to put that in square. 1, 3, 40. Press enter. I'm going to look at it again. That's it now. For those who have not had too much sugar in the drink or perhaps any spirit, can you confirm that we now have the right track?
Yes, sir. You have to
So,
look
Yes, sir.
all right, cool. So now we're now going to do the step 2 system G1. It took quite a while, didn't it? See if we can get this thing coming up now. Interesting. I'm not sure if can you see the plot? Can you see the plot?
No, sir.
No, sir.
That's well, it's interesting. A different window is done in. So let me go have to probably stop this and then bring up. Share. All right, so you should be able to see it now. All right, it's quite a journey, isn't it? So here we're now seeing the two plots. We saw the first one with G1, and this is the blue one where you see that I should be able to put in something here. System characteristics. Let's put in, we're interested in steady state. All right, so we'll put in steady state and we'll put in, what else? All right, that's it. So we can see here, when I click on this point, you see the final value, they're saying final value in MATLAB, but what it really means, the steady state point. And from that, we can determine steady state error. Okay, so we see clearly the steady state error is 0.5. Let's go up here to the second system where K was equal to, or K is equal to 19. And you remember that the steady state error was 5%. And clearly we're seeing that the final value or the steady state value is 0.95, which simply means that the error in that system given a unit step, or sorry, a unit step input, the steady state error would be 0.05. So it's consistent with what we have been doing using a very straightforward mathematical approach. All right. Any comments or questions on that before we proceed back with the lecture?
Boy, so this should have take you for the last lab submission.
I'm sorry, could you go again, please?
No, I'm saying that the lesson plan that you're teaching now, sir, was a
Uh-huh.
part of a submission, a lab that we did, I think, in last week. That was due last week.
Oh, so I'm supposed to be verse on this then. This is a piece of cake. So here I'm dropping over myself with the thing. So yeah, I'm so it was fine, right?
No, sir. I
Hello.
believe what he was saying is
Yeah.
that it would have been helpful if this came
Oh, I
before we
follow.
actually did
I
the
follow.
lab, so
Yeah,
that we would
yeah.
have had a better understanding of how to do those calculations, etc.
Understand. Despite best efforts, these things will happen. But I do acknowledge what you just said. Thank you for pointing that out. This line is a bit poor on my side. I don't know if it's the same on your side, but I couldn't hear him completely. I thought he had said that it was the same thing that he was doing in lab, but apparently he said that they had did it before, but it would have been more helpful if he was exposed. Fair enough. Fair enough. All right, but just to point out again that sometimes it's not possible for us to do that based on how things flow. We try our best, but it doesn't always happen. But I'm sure that you're able to appreciate what were the objectives in the exercise. All right, so I'm going to go back now to um, the presentation. Uh, so we just verified that the result of this exercise corresponded simple mathematical procedure, and we're able to get results without using a software. So now let's continue. We are now going to look at the steady state error due to um, a disturbance. And again, we're looking at a unity gain feedback system. All right. Here, though, we are separating the controller from the plant to introduce the disturbance signal. All right. So the steady state error due to a unity step disturbance is given by the expression here. Where's my pen? E of S, or sorry, E subscript SS, the steady state error is equal to the limit of what we have here, 1 over the reciprocal of G of S plus GC of S. Need to note the difference between the two. GC is the controller transfer function, and G of S, or G by itself, is the transfer function for the plant. All right, so that must be understood. And so we're going to now appreciate the um, calculation for the steady state error due to a unit disturbance. So let's proceed with this. So here it is, in fact, the same system, but now we are separating the it's the same system if you look at it carefully, but we're separating the plant from the controller. So g of s would be 1 over s squared plus 3s plus 2, and the transfer function for the controller, gc of s, is equal to k. So here we're going to find the steady state error due to a unit step disturbance for the system in k equal 5, and we're also going to find the value of k that is required for a unit step disturbance steady state error of 2%. So hope that we have appreciated the whole thing about disturbance. It's almost like if it is that, um, let's say, uh, again, I think the last thing I gave was with a drone. Let's say you are operating a drone, and drones are used and becoming quite popular now in everyday life. People using drones to do videography and photography and um, transport um, packages and so on and so forth. So here, let's say you have a drone, and the drone is hovering, and maybe it is picking up I said payload, maybe it's picking up a package. And so that package it's hovering. It's supposed to maintain its position while it's been loaded with a packet. So let's say you are putting something on the drone. Let's say you're attaching a camera. The drone is hovering and you're attaching a camera onto the drone. And in so doing, it would introduce a disturbance. It's like a step disturbance. That camera has a weight. And when you suddenly, when I say suddenly, I mean you attach it and release it. It's like a step disturbance where it is now going to be pulled down by a certain signal, which is going to be the weight of the camera. And so that's a step disturbance. What we would love or what we would expect is that the drone recover from that disturbance and go back to its original position. Now, what we'll see in the coming weeks is that that is not going to be the case. We'll see it here a little bit though. That's not going to be the case in all types of controllers. All right, the algorithm that determines what happens, that is not going to happen all the time. What I mean by that, it will not always go back to where it was, depending on the algorithm. So let's look at this system here that we have. So we have a step disturbance for the system. Let us analyze what's going to take place. So we recall that the steady state error, as it relates to the unity gain feedback system, is the limit of 1 over the reciprocal of the planned transfer function plus the transfer function for the controller. That is all over, sorry, on the 1. So let's substitute. You will recall that this part here, g of s, let's get the pen up, is equal to, let's see if you can remember that, that was s squared plus 3s plus 1. All right, that was the case.
Was it +1 or +2?
In fact, it was +2. Thanks for those who are not drinking sugar drinks or anything strong. So that is s squared plus 3s plus 2. That was what that would be. And we agree that GC, right, GC, the controller gain, is in fact, let's go back up and verify that. I think we said that k equal 5. Okay, great. So the k is equal to 5. So let's come back now and see what that translates into. So again, that just went. So if I could just do this just to ensure that persons are appreciating what's going on. So s squared plus 3s plus 2. All right, and then we're going to plus this with our 5. All right, that's k equal 5, and that is in the denominator. So how do we simplify that? How do we simplify that?
So let S equal 0.
Sorry?
Do you make S
Are you
equal
seeing
0?
how? Are you seeing how? So watch me now. This is just, you see what we have here? And by the way, I hope we need to reciprocate this. See this part here? Boy, acknowledge along there today. But anyway, we're reciprocating the transfer function for the plan. So therefore, this will no longer be 1 over what is here, but it will just simply be what is here. All right. So that now becomes very straightforward. We're reciprocating what I just wrote, and so that being done, we end up with this plus 5. That's not difficult. That's not hard to understand. So therefore, it becomes very straightforward that the function becomes, when we take the limit s approach 0, it becomes 1 over 7. So that is now the steady state error when we have that unity step input disturbance. Sorry, unity step disturbance. There's a difference. Unity step disturbance to the system. All right, the system will not entirely recover. I hope we recognize that. So the system will not recover. How do we know that? Because we have a steady state error of 1 over 7. All right. So if it is that the system was even having an error before, this unit step is going to now add contribute to that deviation. Okay. So the calculations done here is not taking into account any steady state error due to step input. Is that clear? This is only due to the disturbance. Is that okay? So now let's look at the situation where we want a 2% steady state error due to step disturbance. And so again, in a similar way, we're equating 0.02, which is 2%, as the steady state error. And we're again substituting the expression here. And so what we find now is that the new expression that we're going to now take the limit of is 1 over s squared plus 3s plus 2 plus k. All right. And so we equate at the point 0.02, and that's what we have right here. And so we simply transpose, making k the subject, and that now brings us to k equal 48. Therefore, for the system to have a 2% steady state error due to disturbance, you have to set k equal 48. All right. Now, you recall what happened in the plot that we did earlier. As we increase k, we notice that the steady state error decreased. All right, we notice that the steady state error decreased. But did you notice also, let me ask you, what else did you notice from the plot? Maybe it was obvious, I don't know. What is this from the plot?
The settling time decreased.
Settling time increase, sir.
Not hearing anything, sir. I'm not sure if it's me alone.
Same on my end, sir.
So, Albert, can't hear anything you're saying, Not sure if you're talking or not.
Oh, yeah, I'm sorry. I'm so sorry. I had an interruption a while ago. Yes, my apologies. Um, yes, so who is not seeing it? Thanks for pointing that out. I'm still in transient response. I've not gotten to steady state yet. Yes, so what I'm trying to get at with this is, say, we notice that by increasing the value of k, we're able to reduce the steady state error. But I'm asking the question, what else is happening to the system response as we increase the value of k? Anybody tell me?
Sir, you're seeing
Sir,
an increase in the settling time.
Yes, all right. You see, you're seeing an
decrease.
increase in the settling time. Is that
It was a
okay? You're just
decrease,
seeing
sir.
let me click on it and see I can see it.
Sir, I'm seeing that the response
Sorry,
to it is
don't lose your point. Don't lose your point. I just want to clarify something before we move on. I just to reiterate something. Just don't lose your point. What we're seeing here is a slight reduction in, I'm sorry, the um, settling time, because we move from k equal 2, to k equal 40, and in my opinion, that's a fair enough increase in the gain. But look at the settling time; it moved from 2.87 to 2.6. It's a very, in my opinion, a very small change. There's nothing significant happening in that. So the settling time does not change significantly due to the increase in K. All right, go ahead with your point. I'm not sure who it is, but go ahead,
Yes,
please.
some concern. So,
Yes,
I
sir.
realize that as they increase the gain, the
Mhm.
response goes closer to the input. So the steady state value will be closer to the input.
Which you're basically saying that you're reducing the steady state error.
Yes, sir.
All right, noted. Is
So,
there anything else that you notice about the plot?
so I don't know if this is relevant, but I realize that there's an overshoot. The
Oh,
the
you
peak
don't know if it's
amplitude
relevant?
increases. The
You would want, let's go back to the drone example. You have a drone and you put a load onto it, or it well, in fact, this wasn't a load situation. This was a step input. So let's say you have a drone and then you set to the drone. I'm sorry, when I say set to the drone, I mean you provide a command to go to the drone. Move from altitude, say 1 meter to altitude 2 meters, and then your drone start to do something like this. Would you want that? By the way, what did the drone be doing based on the red plot? So here I'm trying to help us to appreciate how to interpret a step response. What does this plot means in reality? So we're using a drone because I believe most persons can relate to a drone. All right, what a drone is and how it operates, but in basic format. All right, basic operation. So I'm saying to us, let us interpret what the drone will be doing if it were that it is following the response of the red line, system G2. Go ahead, please.
sir,
Stabilize
it will be
itself, sir.
Well, the two systems actually stabilize themselves, which simply means that after a certain time it settles down to somewhere, so it stabilized after a time. So both systems did that. I think I heard Crosby coming in. Thanks for that point, but I want us to think about this. Go ahead with the comment. Somebody had another comment to me.
yes, sir. I was saying, for instance, if you tell it to go a certain distance, it will go over that distance and then come down.
All right, I'm happy you said it because you were saying earlier that you don't know if it's significant. So
It's a
having
bit
said that, do you deem it to be significant? Do you
very
believe
much
it's
so, sir.
significant? Yeah, it is. It is. And so these overshoots could mean it's going to crash into something that is probably above it. If it's in the house, or if it's in an arena you're flying or in a closed space, then clearly that that looks like over 40% overshoot. It is going to end up in the ceiling. Yes. So yes, it does matter. And we're seeing beyond the overshoot. What else are you seeing?
Sir, the peak amplitude and time. Uh, the time is you have less time to reach the peak amplitude.
Less time. If you're gonna compare, the other one doesn't have a peak amplitude because it doesn't necessarily it didn't. There's an overshoot. Let me do something here. I don't think there's any significant overshoot. Peak response. Yeah, a slight overshoot. There's a slight overshoot. Um. All right. So you're saying that there's a shorter time for the peak overshoot. All right. Let's note that as well. All right. So that is noted. Anything else you want to point out in the plot, particularly comparing the blue and the red plot? Anything of significance that you're also observing? Yes, we're seeing a significant overshoot. What else? And we're seeing that the time that it takes to get to that overshoot is much shorter than that for the blue system. What does that mean, by the way? What does it say to you? Just share your thoughts. I mean, we can't be wrong here. We're just sharing our thoughts. I'm trying to see how you're analyzing the system response.
Sir, the system is more stable, more um progress more steadily. I don't know if that's the right way to say it.
And which one are you speaking of?
The blue system,
It's more. It is. What do you say?
G1,
It's
system
progressing
G1.
steadily. All right, noted. I would like to hear some other persons in the platform
So
on the. Thanks for the comment. I'm gonna respond to your comment in a while, but I want to hear from some other persons before I make that comment.
The blue, would it be safe to say the blue system that is G1 would have a more steady response to our input, or a more favorable response to our input to our disturbance?
All right. So let me just correct for a while. What we're looking at is not the disturbance plot, but the one that we did earlier for the steady state error due to the unit input. Remember that unit gain feedback system? So it's the same system, but what we're looking at right now is the steady state error due to a step input for k equal 1 and k equal 19. But the questions I'm asking right now is for persons to share how they interpret the plot that we're looking at. This is very important because I think perhaps in the lab that you'd have done, you should be able to state what the system would be doing. And this is what we do because this is now simulation. We don't have the drone before us, but we can look at what we're seeing here and analyze what the drone would be doing. So that's basically what I want to pull or to have you share at this moment. So yes, just to go back to what we have already agreed on, no significant change in settling time between the two systems. Okay, but there is a significant overshoot in the higher gain system, significant overshoot compared to the other one. But there's something else that um, is so linked to overshoot that I wanted to take from this plot. All right, remember I can't see the share feature, the raise hand feature, so
Hello.
just go right ahead because I'm looking at the MATLAB plot in full screen.
So why my computer decided to freeze up now?
Yes, go ahead. I'm hearing somebody coming in. All right, let me come back down to here where I can perhaps. Who wants to speak?
Hello.
Yes, go ahead, Travis.
Oh, yeah. Does the plot show that the drone is moving faster to the amplitude in the red because of the rise time?
Correct. That's correct. That is a
That's
more
good.
responsive system. That's one other thing. Thank you for that. It's more responsive. I think somebody was alluding to that earlier as well, in different words. So it's a more responsive system. Okay. Um, there's something else. I'm interested of time. I'm going to actually tell you. Um, the system is now exhibiting oscillatory response. Oscillatory response. So we're seeing that we have an undershoot, we have an overshoot here again, and I have a slight, we have about two overshoots. What typically would happen when you have a very high overshoot that the system will have a lot of oscillatory behavior. All right. So if you think of the drone, just put your hand up for a while and just level it and move your hand in a similar way to what you're seeing there. And that occurs in like about this frame about 2 seconds. 2 seconds, move your hand up and down 2 seconds. But let's say if this amplitude that we're looking at was in meters, then the drone would have been commanded to go to 1 meter, but instead go to 1.4 meter. So it's 400 centimeters over the required point, and it dances a bit before it settles down to that point. So imagine the drone doing that kind of a behavior. Certainly that is dangerous. And then beyond it, it has the oscillatory behavior. So then it went up and then quickly went to its new position. But it had some amount of oscillatory behavior, which lasted for about 2.5 seconds before it settled down. All right. So these are some of the things that we want to be able to extract from a system response curve. What would be nice is to actually have a system that we can look at physically, and we can use some software, and those who would have done instrumentation systems would recognize about the data acquisition systems where we can acquire the amplitude. Let's say if it's the drone, it could put on these things, and we can analyze the actual behavior of the drone against simulated results. And it is a standard practice in engineering, where once you do your simulation, you do your design, having implemented the system, we can then compare our simulated data with that of the actual test data to see how close the two models agree. That is a standard way to do it. All right. All right. So I'm going to now go back to the rest of the slide. I hope that persons are any question before I move on from this. or comments? Okay, so complete this presentation. All right, so let's go back to our problem here. So when we spoke about the steady state error due to the disturbance, step disturbance, we saw that with a value of k equal 5, we had a steady state error of 1/7. So here we're seeing that the system did not recover from the disturbance. Are we seeing that with this particular system, it didn't recover from the disturbance? Yes, we saw where when we increased the value of k from 5 to 48, we're able to reduce the steady state error due to disturbance significantly, right? Reduce significantly. But the reason why I went over to show you the plot again is that when you increase k, even though it has a positive effect, meaning that it reduces steady state error, but it also causes another problem, which is the significant overshoot and stuff like that. So if you were to say by just looking at the outcome here to say, okay, let's keep increasing k until this thing goes down to near zero. No, it doesn't work like that, because while you're doing that, something else that is not supposed to happen, or something that's not supposed to happen, is happening, which is the effect on the overshoot. All right, just bringing your attention to that. All right, so that will complete the presentation for today. I am hoping that, by the way, next week is a scheduled test. I should have come a little bit earlier, but what I'll do is address any questions that you may have. There's a worksheet, excuse me, the worksheet posted that in my estimation. Let me see if I could bring it up quickly. So before I go to the worksheet, are there any questions that person want to ask regarding this presentation?
Yes, sir. One question.
Go ahead, please.
Sir, based on what we just went through, would it be that increasing K increases the responsiveness, and at a certain point it will be overly responsive or too responsive?
That's in fact correct. All right, so increasing K increases the responsiveness of your system. But is that responsiveness that contribute solely to the overshoot? Is almost like, I don't give an example, but that is in fact very, very correct. The system becomes so responsive that it overshoot its target. It's moving off so quickly, it's not able to recover and slow down. All right, so it's almost like if a person is moving off quite quickly to achieve a particular position control, and you're not able to stop where you're supposed to stop, so you end up passing the position because of the excess energy and speed, and then you try to go back again to that new position and end up passing it again until after some trial you're able to settle down at the point. So that's another way of looking at it. But long and short, I'm agreeing what you said. But by increasing the value of k, the system becomes very responsive, and there is a point at which the system becomes way too responsive, and you have excessive um, overshoots. And I'm going to go further, that if you continue to increase k with some systems, what do you think is going to happen?
It crash, sir, malfunction.
Well, I'd prefer a control system term.
Let me think about it then, sir.
S, start with S. Well, it has to do with S, stability. It becomes unstable.
Unstable, okay.
Yeah, man, it becomes unstable where it just, as you said, crash. That's ultimately what will happen. It will try to achieve an amplitude that it is outside of its bound. When we spoke about stability, we're saying that the output is unbounded. So if it is that you are doing a drone and the drone becomes unstable, yes, it is going to probably start shooting off into the air with increasing amplitude, or begin to go back and forth with increasing amplitude where it's now started going way outbound. So it is now gone out of control, all right, in the way I've just described it, right? So yeah, that is one way. If crash is a term that you use when you speak about in the context of it going, trying to achieve a position that is way out of its limit. All right, unbounded, it will continue to increase. So if, let's say, for argument's sake, the drone was allowed to continue to go back and forth and increase in amplitude, it will keep doing that until it's in space, if that were to be the case. But ultimately, we know that the drone is going to lose power, it's going to burn out something or something of the sort. So it will now, as was just explained, crash. But the term stability, as it relates to theoretical context, need to be understood that the system will try to achieve infinite output when you apply a finite input to the system. BIBO, bounded input, bounded output. All right, so thanks for that question. Any other concern or question that you want to raise before I move over to addressing any worksheet concerns? All right, that sounds like a no. So let me see if I could quickly. Persons would have seen the worksheet, I believe. All right, don't answer that. Don't answer that. Let me bring up the worksheet and just worksheet. Let's see. No, this is not what we want. Let's bring this up here. Close this. All right, so I'm trying to bring up the Blackboard Collab worksheet. Which, for some, are you seeing a shared screen right now? Hello?
No,
No,
sir.
sir.
Yeah, because I just lost. All right, let me bring this again here. I just lost my okay, let's try again.
You said worksheet number 3, sir?
It's not, I don't know if it's number 3. I honestly don't remember the number, but it's the one that is on the unit that we're
4,
now
sir.
doing, system. And that might be what we're looking at here. So I am going to now try again. All right, this should do it. All right, so here is the worksheet number 4. And worksheet number 4 has questions that would cover all the topics that we would have covered in that unit. So therefore, I'm saying to us, based on the statement for the test next week, 1 hour test, these are typical questions that you'll be asked. Not saying that you won't be asked questions outside this, but it will fall within the unit. So these questions, I'm asking you to practice them as you would have been doing for the ones before, in preparation for test number 3. Just looking at it, because my impression that persons wouldn't have yet given much attention to the worksheet. I tried to post it a little earlier, but it was posted, I think, over the weekend, maybe Thursday or Friday, I remember. But what you're seeing here is nothing that we have not covered. We looked at, I remember doing something that is where we actually extracted certain parameters for a system. All right, so let's look at the first one and just to sort of put things in context. So here we're saying evaluate the roots of the system. Sorry, by evaluating the roots of the system, sketch the expected step response. So here we're talking about a system that is fully defined here. This is the complete description of the transfer function. Okay. Now for the first one, g of s is equal to 10 over s squared plus 2. Can somebody open the microphone and share just by looking at it? You look at what are the roots in this expression? What are the roots in that expression?
That could be what,
2 and minus 2, sir.
This is 2 and minus 2. Anybody else want to share on that? What are the roots? I note it. I hear you. I want to get some other feedback on this. What would be the roots of this here system? All right. So what you probably realize is that you can't quickly pull it out like that. But I want to tell me how would you find the root of the system? Or you could, in fact, can I tell you? You don't necessarily have to find, well, you're supposed to evaluate the roots. Again, I can't see, I'm not able to see who is raising hand. I hear the beep, but I can't see because of how I'm looking at the screen right now. I'd have to go across to look at it and come back. But I just go ahead and share your point or your question, please, or your response.
Oh, no, sir, it's art. I realized that I would have been wrong.
Oh, so what you're going to see is that the roots of this expression, all right, first of all, are the roots on the left hand side or on the right hand side of the imaginary axis?
So it's on the left.
Left hand side, sir.
So is it stable or unstable?
Unstable.
It's on the left. If it's on the left,
I agree with you that it's on the left.
It's on the left.
And so is the system stable? I hear you say it's not stable. Why would you say that? Given that the poles are on the left hand side of the
If
imaginary
it's on the left, it's stable.
So we want to remember that once the poles are on the left hand side of the imaginary axis, or another way to put it, if the real parts of the pole or poles are negative. All right, but how would you find? I want someone to tell me how would you find the poles of this? Because this is a question you have to ask. You'll be in the test doing a question similar to this. How would you find the poles of the system? Tell you what. Everybody gone silent. All right, is after 8:30 now. So
So
Sir,
find
I
the
am.
root
the
of the
poles
denominator.
aren't the poles the values that drive it to zero, sir?
I'm sorry. Could you repeat?
Aren't the poles the values that will send the equation to zero?
The poles of the system are any value of s that will make the transfer function. No, sorry. Did you just say zero? It's
Infinity,
not
sir.
zero. Infinity. Yes, yes. So let me be clear. Poles are any value of s that will cause the transfer function to tend to infinity. And how we extract that is that we look at the denominator. Where's my pen? I'm not able to mark here. We focus our attention there, which is the characteristic equation. Excuse me, characteristic equation. What I'm saying to us, without calculating it, just tell me, just share with me how
Sorry,
would you
sir.
find the pole. Go ahead,
So in
question,
this
comment.
case, if the denominator is zero, wouldn't it be going to infinity?
We're not trying to make the denominator equal to zero. Oh, I'm sorry. I'm sorry. Yeah, I'm agreed with you. Yes, we do want to make the characteristic equation equal to zero. And that is what we're trying to do. And in so doing, the function will tend to infinity. So that is correct. I'm agreeing with you.
Right.
So what
That's
do you
what I
then
was
say?
saying initially, sir.
Okay, all right. So based on what you're saying now, I'm agreeing with you. That's what we want. That's what we want. So the question I'm asking is now, how do we find the poles? How do we find the poles?
with the
Sir,
pole
equate
with
the denominator to zero.
imaginary number.
All right, I heard two persons. Uh, let me come back to.
So you don't make s equal to -2.
No, it's not s equal -2. I think it's
So
probably.
use the quadratic formula.
You would
You see where we're
equate the
going
you would,
now. So
you'd
so
equate the
I'm hearing two
numerator to
responses.
zero, sir.
Correct. You do that. And so if you have s squared plus 2 equals 0, what is that telling us? S squared is equal to -2. Isn't that true?
Yes,
S
sir.
squared equals
Correct, sir.
-2. No, you can't find, well, let me be correct. There's not a real solution to this expression. You follow what I'm saying? So we know it's going to be a complex number. What did I hear a while ago? I heard somebody saying that you use the quadratic. What somebody was saying? So that's, I'm agreeing with you what the person who just spoke a while ago, that you equate the denominator to 0 and solve. So here we have s squared equal minus 2. And clearly, the solution to this is not a real number. The other comment is about using the quadratic equation. Can that person come back online, please, and just share a little bit more about that? Hello? All right, so who want to pick up on that comment? Who want to find the roots? And I have no control. Well, in fact, I can't control whether I use a calculator or not. The truth is, I write the paper with that in mind, that persons will use a calculator. So if you have a calculator, but beside the calculator though, for the fact that we need to be able to do this by hand, can somebody tell me how do we find the poles in this expression? How do we find the solution to s squared plus 2 equals 0? How do we find the poles? All right, tell you what, that's a homework.
So,
That's homework.
sir, wasn't that what we just said when we just said a while ago, sir? You equate x squared plus 2 to 0.
All right,
So
don't
you
come
can't
S.
find the root of the
don't come
denominator.
offline. Don't come offline. Having done that, s plus 2 equals 0. What's the next step?
Right. So then you'd know that s would be equal to either 0 or minus 2.
I'm sorry.
So
S equal
the
what?
poles would be 0 and minus 2, sir.
Really? How you end up with that?
Sir, by equating the denominator to 0, s squared plus 2 equals 0.
All right. So stick with that. S squared plus 2 equals 0. And then what's your next move? We're finding
Then you
S.
carry
We
the
want to make. Good.
you
S squared
factor
equal
out
what?
s.
Hold on. S squared equal. Continue.
Minus 2, sir.
I want to thanks, Connie. I want to hear the person online. I can't see the name now, but because of what I'm sharing on the screen here. But I want to go ahead with it with your solution. So you have s squared plus 2 equals 0. You carry over the 2. Continue, please. What do you have? S squared equal what?
The square root of minus 2.
All right. So you have the square root of minus 2. How do you reckon this now? I mean, of course, you can find a solution, but it's not going to be real. So go ahead and tell me
They're
the
going to be
solution.
imaginary, sir.
So tell me what they are.
So it'd be minus 2j or
There are two
j2 or i2
all right.
and 0.
No, minus. Go again for me, please, with that solution, please. Minus what?
Minus 2j.
You sure it's 2j?
Or 2i.
When I use I or j, that's fine. I could use either one of them, but that's not where the problem really lies. Look at the fact that we're using s squared equal minus 2. So what we need to be careful of what that square is saying. What we need to do here is to find the square root of 2, but with the complex notation before it. So wouldn't that be 0 plus I root 2? And the other one would be 0 minus I root 2?
Yes, sir.
All right, so be careful on the calculations, because this is something that we should be able to do quickly by hand. All right, so we have what we call complex conjugate solution. So don't come off the line. All right, by evaluating the roots, sketch the expected response. Can you describe to me what you expect the response to look like? Can you describe that? Because you can't draw for me right now. Well, at least I don't want you to draw. So we're not going to share the screen. How do you think it would look based on look at these poles? So this one perhaps shouldn't be the first one, but nevertheless, you're accustomed to challenges. Note where the real part of the function is. Where is the real part of the function?
At
When
zero.
you read at zero, it is at zero. And when we say at zero, it might sound casual, but do you see any issues with it being at zero?
No, sir.
Really? What do we say when we have the real part sitting on that boundary line? What does this behave? What's going to be the behavior of the system? Sitting on the
Oscillator.
boundary. And could you be a little bit more specific? It will be
Um.
oscillatory forever.
Oh.
It will never die down. So we have to distinguish between being oscillatory and being constantly oscillatory. Because, of course, you can have an underdamped system being oscillatory, but over time, as time progresses, it settles down. But when the system has a pole that is sitting or is on the imaginary axis, remember you're going to have the system will oscillate with what? Constant amplitude. And we don't want that in control systems. So that's exactly what will happen to the system in the first case, G of S in the first case. The system will oscillate with constant amplitude. Why? Because we have the real part of the poles being zero, right? And it's sitting on the imaginary axis. So that's what's going to happen to it. Right? And it has complex parts, so therefore it will be oscillating. In fact, that's the only solution. Once it has real parts sitting on the imaginary axis, it's going to be a complex number. That I can tell you. And it will therefore be oscillatory. So we get the gist in terms of what is expected here. Evaluate the poles, and from that, we know the whole rules already in terms of saying if you have poles that are repeated, you're going to have oscillations, but you can have a number of things happening. You can have system being let's go back to the fundamental. For a second order system, you can have the system being um, underdamped, overdamped, critically damped, or in this fourth case, the system can just simply, well, five cases, the system will just oscillate with constant amplitude. And the fifth case is where the system is unstable. All right, so those are all the possibilities in terms of the pole location. Now look at the third example here. We're seeing a third order system. All right, and so what I'm expecting here is that we would evaluate all the poles, and based on our discussion about dominant poles, we'd see if they're dominant poles, then the system can equate to a second order system or perhaps a first order system, who to tell, all right? But we can clearly see that one of the poles would be at minus 20, all right? So just to point that out. The second part here, going through the paper generally to point out any errors that may raise some concerns. Consider that persons have not yet given much attention to the worksheet. Part B is to determine the system gain and settling time for the system following systems. All right, so this here is a first order system, and so we remember the general expression for a first order system. Can somebody remind me of that? Okay. Body, system gain over tau S plus 1, right? General expression for the first order. And you also need to remember the general expression for the second order, all right? Part question 2 says determine the settling time, peak time, steady state, error, and maximum percentage overshoot for the unit step response. I could make this interesting, but let's see. Anybody can guess the overshoot, percentage overshoot? Not guess, sorry, did I say guess? Not guess. Can somebody approximate or evaluate the percentage overshoot?
So would it be about 13.5%?
Okay, so here 13.5%. That's interesting.
They're about 35%.
All right, so I have to be careful. I hear 13 0.5, here 35. Can I get some more feedback? So note it. Can I get some more feedback as to what it is? Look at the point at which it's going to settle. All right. Question is,
I think about 35, so erase that. It's more like 13 point, more like 13.5.
okay. Anybody else? So what is this distance? What's that distance? Not percentage. No, what's that distance?
Overshoot, sir.
Yeah, man, but instead of a value.
Zero
So,
point 035.
all right. So this distance here is 0. Go again. All right, something like that.
Yes, sir. Yes, sir. Something like that.
Okay. So that divide by 0.1, yes, multiplied by 100. How much do we get?
So it should be 0.35.
I'm sorry, could you repeat it?
It should be 0.35.
All right. So we have 1 here, 0.1, yes. No, I'm sorry. What do you mean? You mean the result?
Yes, sir. Result.
You're saying the answer will be 0.35? No, man. Let's get this straight. Remember,
So is
I'm
it
about
about
sugar in my drink, you know. I'm have sugar in my drink, so make sure that I'm gonna have no sugar, no rum in that food and drinks. So talk to me proper now. We agree that the distance between here, so yes, is that correct?
Yes.
All right. And so we're now putting that over 0.1. So that is going to be what? 0.35. Is that correct?
35. Yeah, times 135.
Yes.
Then multiply it by 100.
Yeah,
What are you going to end up with?
35.
Well, I understand I could have gone to sleep. I'm not stressing no more. All right, 35%. That's what I got. Are we agreeing on that?
Yes,
Yes, sir.
sir. Bring here me a while ago, sir. I use calculator.
No, man. Well, you know, I tell you to use the calculator, but try and use the thing on top of your neck. All right, use it up as well. So it's fine. Hmm?
I was saying for some reason I saw 1 and 1.14. That's why I said
Okay, yes, yes.
13.5%.
So yeah, and I understand. You probably had something strong in your drink as well. So we're not going to stress it. But the fact of the matter is we have to be careful. I know your test is in the night. Sometimes persons have a long day. Um, I had a long day myself today, but as you have seen, the test is. I try to make the test as objective as possible. I try not to make the questions too in depth because what is going to happen is that if you make the slightest mistake, you're going to be losing a lot of marks. If it were that I were to do that, to give you a long simplification problem and then you make one simple mistake, boom, that's it. So I try to keep it like that without trivializing the difficulty level. And so it's a challenge for me to do that, but I'm still trying at it. So point I'm making here is just be careful not to make those mistakes. And it come by doing practice, right? Practice. And in the event that you make a small mistake, it should not significantly impact on your final grade. That is how I've tried to make. So more questions will also help in that regard. All right, so I'm going to stop here for tonight. In my opinion, I believe the questions are manageable, something that you can go through the notes, or you could pull a basic textbook and what is this? And make that evaluation. Look here, cross this off for me, please. Obviously, you wouldn't do that. Draw the root locus plot for the system. So this is not required at this stage. So persons might be saying, draw root locus. What are we talking about? So that's not a part of the system, okay? I thought I took this out. Terminal value of k. So don't do that part, all right? this part would not be applicable as well. All right, so that is it for this afternoon.
Sir,
Yes, go ahead.
in terms of from what lecture to what lecture is the test?
All right, so if you look on the platform, you'll see, I'm hoping that you can see, because that's how I put it, you should be able to see the test outline, meaning that you'll see the test date, you'll see the test topic, test number 3, third 20%, and you'll see beside it topics in, or should I say, let me just bring up the page so you can see where I'm talking about. If I could do that quickly. So to answer your question quickly while I'm doing that, it is unit, all the content of unit that speaks to system response analysis.
Sir, you said we won't be required to we don't have to replicate the matrices or anything like that. You said you won't be testing us on that, but it's just knowledge.
Matrices, where did that come from?
From last lecture.
Matrices.
Where you put the system into its they call it.
State space.
Remember what you call it? Yes.
I did state space last week. Is state space with the, I'm asking a rhetorical question. Is state space with the last week?
Or the week before?
All right, put it this way. The items for the test would be on system response analysis. So I'm not going to test you on anything
outside. All right, sir.
Yeah. If you wanted to change, you can just say it, just say the word.
No, that's fine, sir.
All right, noted. All right, so I'm gonna stop now. You can go on there and look. You should be able to see it. It says on the thing, test 3, unit topics, unit 4 topics only. All right, that's what it says.
No problem, thanks.
Yeah, man, 60 minutes. All right, so keep safe, and all things being equal, we catch up next week. I'll let you know if we're having a class after the test. All right, so
all right,
take care. Next week, cool.
All right.
All right, take care, man. Cool.
All right, sir.
All right, please be safe.